All right, we are actually going to take a look at section 11.4 today, which is about spheres. And depending on which year you're watching this, we might be doing this out of order and coming back to 11.3. Just because they don't need to go after one another, this section is shorter and fits better with the time that we have. So 11.4 is all about spheres. And this is the only section where we're going to worry about the volume and the surface area of that shape. The rest of the shapes we learn in this chapter, we're just dealing with the volume of those shapes. But for spheres, the volume formula and the surface area formula are really closely connected. So the volume of a sphere, you might know this formula already, depending on whether you learned it in middle school. The volume of a sphere is going to be 4/3 pi r cubed. And that's really interesting for a few different reasons. The main thing is, hey, this is the first and only formula that has a cubed variable in it. Why is that? Our other variables are usually squared and multiplied by the height. But if you think about what a sphere is, let me see if I can quickly draw a three-dimensional sphere here. Good luck, Miss Goring. When you think about what a sphere is, it has a length that is defined by its radius or its diameter if we're doubling it. It has a height that is defined by that same amount, radius or diameter if we're doubling it. And it has a depth, kind of think about that coming straight towards you, that is also r. So to get 3 dimensions, we really are doing length times width times height when we do radius times radius times radius. That's why we've got 3 of them. We don't have a different dimension to use in our formula. We only have the radius going from that center point to everywhere in the circle, right? 4/3 is interesting as well. Example 1 is a video talking about this. We're actually going to skip it because we did not do 11.3 before this, so it's going to make a little bit of confusion happen if we watch that video. We'll watch it when we have a chance. But it gives you the reason why the volume formula for a sphere is using this fraction 4/3 at the front. The surface area formula for a sphere is one that you may already have known as well. The surface area of a sphere is just 4 pi r squared. And interestingly, volume and surface area formulas for a sphere are really, really closely related. Like, it's very obvious why the volume and the surface area spheres formulas are like this, but it's not obvious until you take calculus. So I can't explain you the relationship between these two, but as soon as you take calculus, you'll be like, oh, now I get it, which is kind of a cool connection that you'll make back to when you were in geometry. For right now, we're just looking at these formulas. So like I said, we're skipping example 1. Example 2 is going to show us how we're using this section to relate the surface area and volume. So the drama club makes a big ball from foam to hang above the stage for a play. They plan to cover the surface of the ball with metallic fabric. What is the minimum number of square meters of fabric the club needs? So the club needs to figure out how much surface area they're going to need to cover this ball, right? We would be covering the outside surface with this fabric. So we need to figure out the surface area. But of course, to find the surface area of a circle, we need to know 4 times pi r squared. We need to know the radius. They didn't give us the radius, but they did give us the volume. So let's use the volume and go backwards to find the radius of this circle. So we can say the volume of 1.8 is equal to the volume formula, 4/3 pi r cubed. And we're going to break this down until we get r on its own, until we find the radius. So the first thing we can do here is we can divide both sides by the unnecessary stuff. In this case, the unnecessary stuff is 4/3 pi. So I'll divide by 4/3 pi on both sides. This can be something that challenges people with their calculators. Please, please, please remember that 4/3 pi should go in parentheses because it's multiple things that are in the denominator of the same fraction. If you don't use parentheses, then it could make very different answers that are not correct. What you should get if you divide 1.8 by 4/3 pi is 0.43. So here 0.43 equals r cubed. We're going to need to find just r. So we're going to need to uncube or take the cubed root of both sides of our equation. You hopefully remember doing cubed roots in previous classes because you've done them before. The cubed root button on your calculator is under the math menu. So you'll go to your graphing calculator, you'll hit the math button, and you'll go down to option number 4, and that option, number 4, is the cubed root option. So if we take the cubed root of 0.43, we find that that's going to give us 0.75. The cubed root of r squared is r. So the radius is 0.75 meters, because we're in meters here. Now that I find the radius, I can use the surface area formula to go from here. I know the surface area is 4 pi r squared. So I have 4 times pi times 0.75 squared. And when I plug that all in and evaluate that, I find that the surface area for this sphere is 7.07 meters squared, right? We're measuring in square meters since we've calculated the surface area, which is a unit of area. All right, we're going to do the same kind of thing, but the other way around. This time we're going to say, I know the surface area. How can I find the volume? So it's going to be very similar. This time I'm going to say 6 equals the surface area formula, 4 pi r squared. And I need to get that r on its own, find the radius. So I'll divide by 4 pi on both sides. Once again, it is highly, highly important that you put 4 pi in parentheses or else you may not get the correct answer in your calculations. When I divide by 4 pi, I should end up with 0.477 equals r squared. And then, of course, I have to take the square root of both sides, and I learn that 0.69 equals my radius. If I'm looking for the largest volume that sphere can have, then I will plug that in. 4/3 pi times 0.69 cubed for the volume of our sphere. And that will give me 1.38 meters cubed because that's our unit of volume. Please make sure, even if you're just following along and writing these down, to attempt these calculations using your calculator and make sure you get the right answers. Because if you don't, then you're going to do other problems wrong as well. And I want to make sure that you know how to do this simple arithmetic where you're just dividing and not have that be what holds you back from getting these questions correct. On the next page, we've just got some problem solving to do with our sphere formulas. So this is an interesting problem. What percentage of a cube does the inscribed sphere occupy? So by inscribed sphere, they mean that this sphere touches the edges of this cube all the way around. So it's inscribed. Every single face is touched by that sphere. So we want to figure out how much extra space is there in this cube, right? Maybe this is a magic 8-ball in a box that's being packaged. And we want to say, all right, I know how big the magic 8-ball is. How much empty space is there? What percentage of this box is full of empty space when I package it like this? And one thing you might notice is I don't have a number. I just have a general sphere and a general cube. And what that means for me is this percentage is going to be the same no matter how big or small this construct is, right? Maybe it's a golf ball in a little cube-shaped box. Maybe it's a basketball in a cube-shaped box. In every case, the percentage occupied by the sphere will be the same percent of the cube. So let's figure out how to find this out. When we find percentage, we need part divided by whole. So first I need the volume of the sphere itself, right? And since we just have r, that volume is 4/3 pi r cubed. Then I need to know the volume of the cube. Well, since I know the radius of this circle is r, then the entire height of it is 2r, which means the height of the cube is 2r. And since it's a cube, the length is 2r and the width is 2r as well. So the volume of the cube is 2r cubed, right? So 2 cubed is 8, r cubed is r cubed, and the volume is 8r cubed. What I'll need to do then is I will take my top number, my sphere, 4/3 pi r cubed, divided by the entire amount of space in the cube, 8r cubed. When I divide these, notice that my r cubes cancel each other out. There's one on the top and one on the bottom. So the calculation I'm essentially doing is 4/3 pi divided by 8. And when I do 4/3 pi divided by 8 in a calculator, I find that that gives me 0.52, leading me to a volume or a percentage of 52% of the space in that box is taken up by the sphere, which isn't great. That's not a super efficient packing strategy. When people ship lots of golf balls or baseballs or Magic 8 balls, they're losing a lot of space in the corners of this box that are empty. Next couple examples on here. Example 3 is really simple. I just wanted to bring it up because it includes the word hemisphere, which of course means half of a sphere. So instead of using 4/3 pi r cubed to find the volume of this one, I'm going to use 2/3 pi r cubed because I'm using half the volume. So 2/3 times pi times the radius of 4 cubed. Easy to evaluate. If I leave it in terms of pi, which I'm allowed to do, that'll be 128/3 pi for the volume of the hemisphere. All right, and finally, we have a silo here. Well, not finally, there's actually another one. But we have a solid here, and it's got a cylinder and a hemisphere. We have some questions about the density of this one. So the density of this solid is 100 kilograms per meter cubed, and we want to know the mass of the solid. So let's do this in a few pieces. We first need to find the volume of this shape. And there are really two shapes here. It's a composite shape. I've got the cylinder. We know the cylinder has a volume formula of pi r squared h. The radius of this one looks like it's half of 2 or 1. So pi times 1 squared times the height of the cylinder, which is 3. Plus we have a hemisphere on the top. And our hemisphere formula would be half of the sphere formula. So 2/3 pi r cubed. 2/3 times pi. The radius of the hemisphere is the same as the radius of the cylinder. So that's 1 cubed. What I can do here then, to keep my work organized, is I can individually find what is the volume of the cylinder, what is the volume of the hemisphere. The cylinder to the nearest hundredth is 9.42. The hemisphere to the nearest hundredth is 2.04. So if I add them together, I get a total volume of 11.51 meters cubed. From there, I just need to figure out how to find the mass of the solid when I've been given its density. And this is something that you might remember from earlier classes as well. We learned a calculation where the density is equal to mass per unit volume. Density equals mass divided by volume. In this case, if I know the volume and I know the density and I need to find the mass, I would set that up as density is 100, because it tells us that in the question, equals the mass I don't know, divided by the volume of 11.51. And then, of course, all I need to do is multiply both sides by 11.51. So 100 times 11.51 gives me 1,151. 1,151 is a measurement of mass, so that is in kilograms. And the mass of this silo is 1,151 kilograms. Fantastic. One more example, similar to the one we did up above, where we have a sphere inside of a cylinder. It says the height of the cylinder is equal to the diameter of the sphere. So this is also inscribed. The sphere touches the cylinder at the top and the bottom and all the way around the center. What is the volume of the space between the sphere and the cylinder? So the unused space, right? So to figure this out, we'll just take the volume of the cylinder and we'll subtract the volume of the sphere. So the volume of the cylinder is going to be pi r squared h. So pi times my radius of 12 squared times my height. The height of this cylinder is the same as the sphere. And we know the sphere has radius plus radius, so the height is 24. We're going to subtract the volume of the sphere, so 4/3 pi times the radius of 12 cubed. And I'm going to do this calculation in terms of pi. In terms of pi, my cylinder is 3,456 pi. And in terms of pi, my sphere is 2,304 pi. So if I subtract those numbers, I find that the total used or the total unused volume, the total space between them, is 1,152 pi, it's still in terms of pi, centimeters cubed. I, of course, could find this as a decimal approximation. You might be asked to do that sometimes. Or you might be asked to leave it in terms of pi, so both forms will work here. Hopefully this helped you out, and you can get started on the assignment about spheres.